Hello everyone, this is SINGH and today I'm going to present my experiment on keyboard interface with LCD LED matrix display using 8085 microprocessor circuit. So this is the innovation video for the course PhD 306, which is microprocessors and microcontrollers. In this innovation, I have used two 8255 programmable peripheral interfaces simultaneously on a single 8085 squared. Okay, so one of the 8255 is for keyboard input and other is for LED matrix output. So in this simulation, what I have done is using the keyboard input, I'm toggling the LED matrix on and off. And the entire LED control was added just by changing 3 lines in the existing program course. So let's go to the slides and I will take you through how and why I did what I did. So let's go. So let's start with the objective. So in this standard experiment here is to interface a matrix keyboard with 8085 squared using 8255 scan for keyboards and display the keycode on the kid's LCD display. This is a part of the standard experiment that is conducted in the lab. Now the innovation I added on top of this is connecting a separate LED matrix to a second 8255 called 8255 and making it respond to every key. When a key is placed, all LEDs is toggle, either off, either on, they all turn off. So what makes this interesting technically is 4 things. First, I use two 825 PCs simultaneously, one for input, one for output, without any control. Second, I achieved this with only 3 bytes changed in the existing code for the keyboard module. Third, I solved a real hardware limitation. 8255's output port cannot be read back, so I use the RAM memory location as a software flag to track LED state. And fourth, the entire LED routine is a self-contained subroutine at address 2050, and that can be cleanly removed or modified without touching anything else. So now let's go to the third slide, and which is system architecture. So let me explain the system architecture for this new experiment. So the 8085 CPU is at the center, communicating with everything through the address and the database. On the left side, you can see 8255 is connected to the keyboard module through a 26-pin FRC cable. Port A of 82551 at address 00H is configured as input. It reads which key column is placed. Port C at address 02H is configured as output. It sends the scan pattern 0 by 0. The control registers of 82551 is at address 03H, and we write 90H to it to set this configuration. On the right side, 82552 is connected to LED matrix. Port A of 8552 at address 08H is configured as output. It drives all 8 LEDs in the panel. The control register of 82552 is at address 0BH, and we write 90H to it as well. In the middle, the LCD display is the kid's built-in display driven by a routine at address 0F4DH. And at the bottom, as you can see, the RAM location 27F7H. This is our software toggle flag. It stores either 00H or FFH to remember the current LED state because we cannot read it back from the hardware. So, moving on. So, how does the keyboard scanning works? So now let me walk through how the keyboard scanning actually works step by step. So step 1 is initializing 8255. We load 90H into the accumulator and output it to port 03H. This port A as input and port C as output. Okay. Now the step 2 is output the scan patterns. We start with the value 01H is raised to C, that's binary 00001, and output to port C at address 02H. This activates the first row of the keyboard matrix. Step 3. Read port A. We execute IN00H, which reads the column data. If no key is pressed in that row, port A returns FFH, the non-key value. If a key is pressed, a specific bit pattern comes back. Now step 4. Encode 8-bit to 3-bit. We call the subroutine at 2038H. This routine takes the raw 8-bit column data and converts it to a clean key number 0 through H, which gets stored in register B. Now, step 5. Display on LCD. We call it 0F4DH, which is our keypad's built-in display routine. It takes the key value and shows it on the LCD. Step 6. Drive the LED matrix. This is an added step. We call 2050H our new subroutine. Toggles the LED matrix based on the plan flag. After all this, the program moves back and starts scanning again continuously. So here the complete program listing from address 2000H. The program starts at 2000H with the label KBD. It initializes 82551 by outputting 90H to port 03H. At 2004H, label init registers B and C as initialized. B will hold the key code and C starts with 01H as a scan byte. From 2008H, label scan, the scanning loop begins. The pattern in C goes to port C. Port A is read. The encode routine is called, and based on the result, we either continue scanning the next row or jump to display disk at 2024H. At 2024H, labeled disk, the raw port data is all together to get the full key value stored at 27F6H. And then the LCD display routine is called at 2028H. Now look at the yellow highlighted row. The address 2036H. Originally this was C30420, which is jump 2004H. I changed this to CD 5020, which is called 2050H. That's the only thing changed with the existing code, just these 3 bits. And later subroutines added. The green row from 2050H onwards are the complete new LED subroutine I added. I'll explain this in detail in the next slide. So this slide shows the core of the innovation, the minimal patch. The entire modification of the existing program is just 3 bytes at address 2036H. Before the change, the 2036H had the opcode C30420, which is jump 2004H. Every time a key was pressed and displayed on the LCD, the program just jumped to init and started scanning again. The LED matrix is never touched at all. After the change, 2036H has the opcode CD5020, which is called as 50H. Now, after every key press in LCD display, the program calls our LED subroutine first. The subroutine executes, toggles the LEDs, and then return brings red rings control back, and the loop continues on. The key point here is that call and red works as a pair. The program flow is not good. The LCD still works exactly as before. Call 1133H and every other visual instruction is completely ambushed. This is what I mean by minimal disturbance, maximum functionality, and with minimal disk. So now let me explain exactly what happens when the LED subroutine at 2050H. When 2050H is executed, the first thing the subroutine does is initialize 82552. It loads 90H and outputs it to port 0BH, the control register of 82552. This sets port A of 82552 as out. Then it loads the toggle flag from RAM location 27 F7H into the accumulator. Now comes the decision. It computes this value with FFH. If the flag is FFH, it means the LEDs are currently on. So we take the yes path, load 00H, store it back to 27 F7H to update the flag, output 00H to port A, it address 08H and all LEDs turn off. The flag is not FFH, meaning LEDs are currently off. We take the no path, load FFH, store it to 27 F7H, output FFH to port A and all LEDs turn on. Both paths end with red, which returns control back to main loop. The reason I use the RAM flag rather than reading port A directly is important. When you do IM08H on this code, it doesn't return the value you previously output. It runs keyboard data because of the port mapping. So reading port A back is unreliable. The RAM flag at 27 F7H is guaranteed reliable software mirror of the LED state. So now let's look at the design decisions I made, and let me tell you why I made those decisions and how I made decisions. First, why look at 2036H? Because 2036H is the instruction that executes every complete successful key press cycle. The key has been detected, encoded and displayed. The clean is guaranteed execution point. Hooking earlier would be inside the scanning loop and would fire even when no key is pressed. Second, why control 90H for 82552? So this was found by experimentation. I first tried 83H, which is the standard mode 0, all the output world, but the LEDs did not respond. I then tested sequence 3E90, D30B, 3EFF, D308, HVD directly from the address 2000H and all LEDs lit up. So 90S is the correct control word for 82552 on this particular code. Third, why RAM flag at 27F7H? As explained earlier, IM08H does not return port A output state on this screen. Hardware read back is unreliable. RAM location 27F7H is a free memory location that we can completely and it gives that we can own completely, and it gives us a perfect software mirror of the LED state. Fourth, why minimal patch philosophy? The existing keyboard and the LCD code was already verified above. Every additional byte I change is the risk of an additional bug. By changing only 3 bytes, I keep the entire proven code base intact and only add new functionality. That's why is second 8255? Because 8255 is fully occupied. Port A is input for keyboard columns. Port C is output for scan heads. There is no free port available. On 82551, second 8255 gives us a completely independent port A for LED. 6 in the last one. Why toggle instead of lighting individual LEDs? When I tried in outputting the key number directly on port A, all LEDs turn on regardless of which key is pressed. This is because the LED matrix on this key is wired in parallel. All the anodes and cathodes are common, but the individual LEDs addressing will provide a different hardware configuration. So toggle all on and off is the correct verified behavior for this hardware. Also, this was an easier way to display interfacing the keyboard with the matrix. If I had to go with individual LEDs, I have to upload code for each. So, for example, if I want to press A on the keyboard and get some pattern, I have to map that into the hardware. So for mapping a LED matrix, you have to have a whole data of how each bit will be on and off for each pattern. So for each of the keys placed, I will have to map a data, which will take a lot of time and generate a lot of memory. So for just showing up this innovation, I stick upon with having all the LEDs turn on and off forever in individual bits. So now we'll have a live demonstration. The video which I recorded will be presented now. So we have made this innovation. So with this innovation, I have interfaced the keyboard module with the 8085 using the 8255 first port, and the first 85 handles the keyboard scanning when the key is pressed. It detects the key press and displays the corresponding code on the kit's display over here. Also, I have used the second 8255 port, which is connected to this LED matrix. When any key is pressed on this keyboard, the light toggles in this matrix. So if the lights are on, this will toggle to off when the key is pressed, and then if it is on, the lights will get off when the key is pressed. So I have entered the program. Now let me execute the code and let's see how it works. So I have started the execution of the program. Now let me press any key on this keyboard module. So the LED matrix is turned on, all the LEDs are on. Now if I press any key, this will toggle again to off. As you can see, this toggled off. Like, we can do this multiple times as well. So now if I again press this will again turn on. If I again press this, it will turn off. Also, the key I am pressing is displayed on this module. So for example, if I press 6 over here, the LCD display on the kit shows 6, and as you can see, this is again turned on. Thank you. Now that you have seen the video, let me summarize it. First, keyboard scanning works correctly. Every key press is rated. Raw 8-bit data is encoded to a clean key number through the subroutine at 2038H, and the result is accurate. Second, the LCD displays the key code correctly using the keypad's built-in display routine at 0F4DH. Third, the LED matrix toggles correctly on every key press. All LEDs switch fully on and off using FFH and 00 output to 8255 port, controlled by RAM flag at 27F7H. Fourth, the entire LED functionality was added within the 3 byte change in the existing code. All the original instructions remain intact. The broader conclusion is that the 8085 kit can drive two independently 8255 PPI chips simultaneously, one for input and one for output, without any conflict. And the extending existing verified assembly code can be done surgically with careful hook point selection to add a new hardware control without risking the existing control. Thank you, and hereby I conclude my innovation video. Hope you liked it. Thank you. Thank you.